Hi, and welcome to C Programming for Arduino, a step-by-step guide. A loop in a computer program is an instruction that repeats until a specified condition is reached. In a loop structure, the loop asks a question. If the answer requires an action, it is executed. The same question is asked again and again until no further action is required. This is called an iteration. A computer programmer who needs to use the same lines of code many times in a program can use the loop to save the time. Most program loops are written to terminate at some point. However, other loops like this loop function you have seen in all of our previously discussed programs are written to run forever. Indeed, to stop most microcontroller programs requires removing power from the board, uploading a new program, or pressing a reset button on the board to stop the current program from running. Now we will not discuss the forever running loop function and its infinite execution sequence. Rather, we want to look at loops that you control with your own code. With that in mind, let's examine the three conditions that constitute a program loop. A loop is simply the execution of one or more program statements. And upon reaching the last statement of the sequence, the program goes back to the first statement and repeats the execution sequence. A loop always initializes one or more variables to a known program state before the loop statements begin execution. Usually the value of one variable is used to control the number of iterations that are made through the statement loop. The initialization condition often involves setting the control variable to 0. This places the loop control variable in a known state. That is, its R value is a known quantity. Some programmers know that a specific compiler initializes the R value of the variable to 0. However, there is nothing in the ANSI standard that requires the compiler to initialize all variables to 0 or null. So the best assumption you can make about the R value of a freshly defined variable is that it contains whatever random bit pattern or a junk value happened to exist at that particular variable's L value. Assuming a variable is initialized automatically to some known state is just not a good programming habit. The second condition of a loop is that a test is performed to determine whether another iteration through the loop statements is needed. Usually, this test involves a relational operator and the loop control variable. The outcome of the relational test determines if another pass is made through the statements controlled by the loop. After each pass through the loop, the expression controlling the loop must change the state. If the control variable did not change the state during the processing of the loop statements, the loop will execute forever. That is, the outcome of the test in condition 2 would never change, which means the loop would run forever. Loops that run forever are called infinite loops. With these three conditions in mind, let's examine the for loop control structure. The general syntax structure of a for loop is as follows. The for loop consists of the for keyword followed by an opening parenthesis. After the opening parenthesis comes three expressions, each of which is separated from the other by a semicolon. The third expression is followed by a closing parenthesis, which is immediately followed by an opening brace. After the opening brace, there is one or more program statements that are to be controlled by the for loop. These program statements are often referred to as the body of the for loop. After the statements in the body, there is a closing brace, which marks the end of the for loop structure. In the loop structure, expression 1 usually initializes the variable that controls the loop. Expression 2 performs some form of logical test to determine if another pass through the loop body is warranted. Expression 3 is usually responsible for changing the state of the loop control variable but is not required to do so. This is the program flow of the for loop. The program begins with the definition of variable k, perhaps followed by some additional statements. Then the for loop is entered. First, expression 1 or k is equal to 0 is processed. Because that expression is followed by a semicolon, expression 1 is a complete statement. Note that expression 1 have a comma delimited list of sub-expressions. For example, you may see something like this. where j is initialized to 1 as a part of expression 1. You can also move the definition and initialization into expression 1 like this. Note that in this example, variable k is defined and initialized as part of expression 1. Once expression 1 is processed, control passes to expression 2, which is k is less than 100. What happens next depends on the outcome of expression 2. If expression 2 is true, and after the statements in the loop body are processed, then loop control is passed to expression 3 where k++ is processed. After incrementing k, control is passed to expression 2 again. Now, if expression 2 evaluates to logic false, then the for loop ends and control passes to the first statement following the closing brace of the for loop statement block. The second type of loop structure you will examine is the while loop. The syntax of the while loop is like this. Notice that only expression 2, the expression that tests whether another pass through the loop statement body is needed, appears as an integral part of the loop's structure's syntax. Obviously, you can still write a while loop. It is just that the syntax structure does not really confront you with the three conditions the way the for loop syntax structure does. Indeed, any for loop can easily be written as a while loop. Let's rewrite the for loop above as a while loop. The first condition of a well-designed loop states that the loop control variable must be initialized to some known state. With the while loop, this initialization step must be done before you enter the while loop because it is not the part of loop syntax itself. This is why we have the statement k is equal to 0 just before entering the while loop. The second condition of a well-designed loop is that some form of logical test must be performed on whatever variable controls the loop. The while loop does have expression 2 as a part of its syntax structure, as can be seen by the expression that appears within the parentheses that follow the while keywords. The third condition of a well-behaved loop is that the state of the variable controlling the loop must change. There is nothing that is integral to the while loop syntax that forces you to write expression 3. You must supply some statement within the statements of the loop body that changes the state of whatever variable controls the while loop. In our example, the statement k++ becomes expression 3. That's all for this video. Thanks for watching. Take care and goodbye.